So when it comes to solving logarithms, we have a lot of rules that we're able to use to our advantage. So let's go over these logarithmic rules. The first rule that I find to be really helpful is if we have something like log base x of a equals n, we can rewrite that as an exponent, right? We can say that's x to the n is equal to a, right? And we covered this in the last video. But if this is all true, what we could also say is that x to the exponent log base x of a is equal to a. So if you have a number to the exponent of log with that number as the base of a number, these two things kind of cancel and you're just left with a. Now, that looks kind of confusing and complicated, and you might think, when would I use that? How does this even work? Let me show you how this works. Right now, this is written as an exponential, right? X to the exponent of this whole thing equals this. Well, if I were to rewrite that as a logarithm, right, you would say log base x of a is equal to log base x of a. What did I just do? Remember, if you go around the horn, you say this to the exponent of this is equal to this, right? So this statement here is true because it's just log xa equals log xa. So of course this is true, it's the same on both sides. But if you go around the horn, x to the exponent log base x of a is equal to a. That's this statement here. So this statement looks obvious. This one doesn't really so much, but they're actually saying the same thing, right? You can get one from the other. And so an example of this, using this rule, which I would implore you to remember, is if you had something like 5 to the exponent log base 5 of 11, and they said to solve this, well, that's just equal to 11. So that's going to save you some headaches and some time if you remember this rule, okay? That's the first one. The next one is what we call the power rule. This one's also very useful, especially when it comes to solving for exponents. The power rule says that if you have log base x of a to the exponent b, you can bring that exponent b to the front of your statement. So this is just going to equal b times log base x of a. So an example of this would be if you have something like 2 is equal to 1.1 to the exponent t, and this kind of looks like one of those exponential problems, maybe from a word problem where you're trying to solve for the exponent, right? Like you have a before and after, you're trying to solve for the time, right? This might be like an investment question or a population question or something like that, and you have to solve for t, right? But it's in the exponent, so in the past we would just use trial and error, but now we know how to take the exponent out of the exponent. All you have to do is have a logarithm here. So what you'll do is take the log of both sides. So log 2 equals log of 1.1 to the t. And then you can bring that t to the front. So you end up getting log 2 equals t times log of 1.1. Right? So we took log of both sides, which is allowed. If you do it to one side, you do it to the other side. And just to avoid confusion here, I wrote just the word log. I didn't write a base. If you don't write the base, we assume the base is 10 every time, okay? So if you look on your calculator and you see the log button, that has a base of 10, all right? That's the standard. Anyway, you bring the t down, and then to solve for t, you just have to divide this thing to get rid of it on both sides, right? So you're going to get t equals log with a base of 10, right? You don't have to write it, but it's a base of 10 of 2 divided by log base 10 of 1.1. And then you could calculate this, right? And you're going to get something like 7.27 if you round it. So that's why this rule is so useful, at least one of the reasons why it's so useful, because it can be used to take an exponent out of the exponent and then solve for it and get a precise answer, right? Instead of having to use trial and error like we have in the past. All right, so that's the power rule. Let's take a look at the next one. This one is called the product rule. Product rule says that if you have log base x of a and you add log base x of b, that's equal to log base x of a times b. Okay? So an example of this would be if you had something like log base 10 of 5, I'm not going to write the 10 because it's just the standard, right? Plus log base 10 of 20. And you can't solve either of these on their own, but you want to put them together and figure out what that's equal to, right? So you could say, well, that's just equal to log base 10 of 5 times 20, which is 100, right? Well, log base 10 of 100, we know what that is, right? You're asking yourself, what exponent do you raise 10 to get 100? It's just 2, right? 10 squared is 100. So log of 100 is equal to 2, all right? So that's where the product rule might come in handy. Now, because we have a product rule, of course, we also have a quotient rule. And you might be able to make a prediction as to what this rule is going to look like. Basically, it goes like this. Log base x of a minus log base x of b is equal to log base x a over b. And really, this you could derive from the product rule, right? Because if you recall the power rule, which says you can bring in an exponent to the front, you can also move an exponent from the front into the exponent, right? So this is the same as saying log base x of a plus, if you take this negative 1 that's here and you move it into the exponent on your b, you're going to have plus log base x of b to the negative 1, right? And if you remember the product rule, this just says you multiply those things together, right? So log base x of a times b to the negative 1. And b to the negative 1, we know what that is. It's 1 over b, right? That flips. So you get a over b. So you can see how we derive this equation, right, from the product rule. It's just a matter of combining the product rule with the power rule, but this really is what you have to remember. You don't have to remember the derivation here if you don't want to. Okay, and you could do an example of this, right? You could say that log base 5 of 50 minus log base 5 of 2 is equal to log base 5 of, well, what does this become? 50 divided by 2, so that's going to be 25. And log base 5 of 25 is just, 5 to the exponent, what gives you 25? Well, the answer is 2, right? So you can solve this, figure out that it's equal to 2, even though you don't know log base 5 of 50, right? You don't know log base 5 of 2, but you can combine them, log base 5 of 25, and you know what that is. And that's how you get an answer. So that's an example of the quotient rule in use. And what's useful is that you can combine the product rule and the quotient rule into bigger questions, right? So if you have something like log base x of a plus log base x of b minus log base x of c, you can combine them all together in one step and say that's equal to log base x of ab over c, because the c is the one being subtracted. So you would just get something like that, right? So you can do multiple at once, okay? Now, the next rule is also really useful. This is called the change of base rule, okay? Change of base rule goes like this. It says if you have log base x of a, that's equal to log base z of a divided by log base z of x. Now, what does this mean? What is z, right? What are all these letters? Well, log base x of a, x and a could be anything. Like that could be a 2 and a 5, a 6 and a 10, whatever, it doesn't matter. But you can change it to have a base of anything you want. That's what z is. Z is any number you choose. And typically we choose z to be 10 because the most practical application of this, I would think, is that if you have like log base 6 of 100 or something like that, you can't calculate that on your calculator, right? Because your calculator only has log with a base of 10. So what you can do is you can use this rule to change the base from whatever funny number it is here to a base of 10. And then you can calculate both of these on your calculator, divide them, and then get an approximate answer, right? That's one of the reasons this is really useful. So let's say I had log base 15 of 26. It's like, I don't know what this is equal to. I don't know what 15, what exponent I have to raise 15 to get 26. I have no idea. But we can change the base. We can say this is equal to log base 10 of 26 divided by log base 10 of 15. And these are both things you can calculate on your calculator, right? And you're going to get approximately 1.203 as your answer. So 15 to the exponent 1.203 approximately is equal to 26. Okay, so definitely remember this one. It's very, very useful. We also have a rule which states the following, and this is another good one to remember. 1 divided by log base b of a is equal to log base a of b. So if you're ever in the process of solving a logarithmic expression and you get to a point where you have something like this and you're like, okay, how do I simplify that? All you have to do is flip the fraction, right? And then the a and the b switch places. So this is absolutely true, and you can use that as well. Okay, and now the last thing we'll talk about is what's called the natural logarithm. Okay, so currently when we talk about logs, you can have log with a base of 10 or, any number here, but this is the one that's on your calculator. You have an actual button for this function. But we also have a button on the calculator, which you might see, that looks like this. It's ln. You might call that ln. This is what we call the natural logarithm, though. And what that is it's log with a base of e. Now, you might have seen me use this e before. I think I've talked about it, and I've said that it's called Euler's number, right? That's what e is. And I think we've talked about where that comes from, right? It's equal to approximately 2.71828, and that just keeps going, right? We've talked about where that comes from, especially as it relates to things like investments, continuously compounded investments. We've talked about it then. So hopefully this isn't the first time you see it and it's familiar, but we will have another video exploring more in depth what it is, what it means, and you should definitely expect it to pop up more in the future. Now, what's interesting with the natural logarithm is all the rules we've learned for logs, the exact same rules apply for the natural logarithms. So in the past we've said like, oh, if you have 2 equals 3x, 3 to the x, and you want to solve for x, you could take the log of both sides, right, log base 10, and then move the x down to the front, right? So this becomes log 2 equals x times log 3, and then you divide both sides by log 3, and you get x equals log 2 divided by log 3, and that's how you can solve for x, right? And that's equal to approximately 0.631. But you don't have to use log base 10. You can also use the natural logarithm, right? If you have 2 equals 3x, you can take the natural log of both sides, ln, and the exact same rules apply. So you get ln 2 equals x ln 3, divide both sides by ln 3, x equals ln 2 over ln 3, and when you divide these numbers themselves are different than log 2 and log 3, but when you divide them, you're going to get the same number because they're in the same ratio. So you're also going to get 0.631. So you have the option, right? You can use the natural logarithm or log, whatever one you want. It doesn't really make a difference.